Welcome back. Let's learn about directional derivatives. Alright, so far when taking derivatives of multivariable functions, we have only looked at partial derivatives, which only consider the slope of a tangent line at a point on a surface in two directions, that being the x direction and the y direction. And if you remember, when we first learned about partial derivatives, I mentioned that we will look at other directions just later on. And well, now is that time. We are going to consider derivatives in any direction at a point on a surface. Okay, because when we were talking about partial derivatives, remember that we discussed that there are an infinite number of tangent lines at a point on a surface. Right, for this point right here, on this surface represented by the function f of xy, we could have a tangent line that looks like this, we could have a tangent line that looks like this, or like this, or like this, and so on. We could continue to draw more and more lines that are tangent to this point on the surface. And so in order to distinguish between these different tangent lines, or the slopes that they have, we have to assign a direction to that tangent line. And so what we did with partial derivatives was restrict a tangent line to be either in the x direction or in the y direction. But now we are going to move beyond that. And so in order to consider directions other than the x or y directions, what we want to do is make use of something that we learned about earlier in Calculus 3 that allows us to describe direction. And what I'm referring to here are vectors, specifically unit vectors, or a vector that has a length or magnitude of 1. Remember that we learned earlier in Calculus 3 that unit vectors allow us to describe direction. We could take advantage of that here. What we'll do is consider a unit vector that is on the plane of the independent variables x and y. So that unit vector may look something like this. I'll label that as vector u. It is a unit vector, meaning it has a magnitude of 1, and it has a particular direction, which will represent the direction for which we want to find the slope of a tangent line at this point on the surface. And really, we did actually do this for partial derivatives as well, just not explicitly. And what I mean by that is this. A partial derivative with respect to x, which we think of as being the slope in the x direction, you could also view as being the slope in the direction of I, the standard unit vector in the x direction. And in the same way, a partial derivative with respect to y, which we view as the slope in the y direction, could be viewed as the slope in the direction of j, the standard unit vector in the y direction. In each of these cases, what we did was restricted the tangent line at this point to be in those directions, the x and the y, by containing it in a plane parallel to either the xz plane, which would be the x direction, or in the yz plane, which would be the y direction. And we will do something very similar here to find derivatives in other directions. We will restrict the tangent line to be in a plane, but specifically a plane parallel to a plane that would be created by the unit vector u and the z-axis. Right? If you think about a vertical plane that cuts through the z-axis in the direction of the unit vector u, that would be the plane that we will want to contain our tangent line in, or really we will contain it in a plane parallel to that plane. That will restrict the direction of the tangent line to be in the specific direction of this unit vector. And so that's the big picture. That's the main idea here with directional derivatives. But how do we actually do it? What does it really look like? Well, let me show you. The first thing I'm going to do here is label this point, which is going to represent the point where we want to find the derivative in the direction of this unit vector. It's the point where we're going to find the slope of a tangent line that has that direction. And actually, I'm not going to label that specific point, but rather its projection in the xy plane. Okay, so I'm just taking this point and basically making it z-coordinate 0. Okay, so we're just taking that point and putting it into the xy plane. I'm going to call that point P1, and we will give point P1 x and y coordinates of x sub 0 or x naught and y sub 0 or y naught. Whatever you want to call them is fine, but those are going to be the coordinates for that point. And then what I'm going to do is draw a line through that point that is parallel to this unit vector. And so that line might look something like this. And so from this line, we could create a plane that is parallel to the UZ plane, the plane that would be formed by the z-axis and the unit vector u. What you want to imagine is another vertical plane that would cut through this line and be parallel to the UZ plane. And so here's maybe what that plane would look like. I'm not going to keep this here. This is temporary, just to sort of help you visualize. But what that plane will do is it will cut through this surface through this point in the direction of that line, which is parallel to the unit vector. And as the plane cuts through the surface, it will make a 2D curve through this point where we could find the slope of a tangent line. Okay, and that would be our directional derivative. And so now I've removed the plane just to prevent things from becoming too complicated here in our picture. But the big takeaway there is that that plane would cut through the surface and create some kind of curve that cuts through that point along the surface. And now we have a curve for which we can build a tangent line. And then what we're going to do next is introduce another point, specifically a point that would be along this curve that's created by the plane cutting through the surface. And so I'm going to put that point right here. And then this point, just like this one, we could project it onto the xy plane or make it z coordinate 0, and that would give us another point down here in the xy plane, which would be a point on this line that we drew through P1 that is parallel to the unit vector. Okay, and so I'm going to call this point point P2. And just so you can still see it, this is point P1, and now we have a point P2. All right, and so then we could draw a line through these 2 points on this curve, which would be a secant line within our plane that cuts through this line. So that secant line may look something like this. And what's important to notice about this secant line is that as point 2 would get closer to point P1, right, if you were to change the coordinates of point P2 such that it's getting closer and closer to being point P1, this secant line between those 2 points would slowly become the tangent line at our original point. All right, in other words, as point P2 approaches point P1, this secant line approaches the tangent line at this point, which would have the slope that we are interested in, the derivative in the direction of this unit vector. Okay, hopefully you can see the similarities to our limit definition of a derivative from Calculus 1. It really is the same idea here. And so for point P2 here, we could describe its coordinates like this. It would be x sub 0 plus some change in x, y sub 0 plus some change in y, right? X sub 0 and y sub 0 are the x and y coordinates where point P1 is. To get from point P1 to point P2, there is some change in the x values and some change in the y values, which would be delta x and delta y, which is why I'm adding those 2 values to those original coordinates from P1 to make the coordinates of P2. All right, and so as point P2 gets closer to point P1, or as this secant line becomes a tangent line at this point, both delta x and delta y would have to approach 0, right? The changes in x and y from point P1 to point P2 would have to approach 0 until those 2 points are the same point, and we have the tangent line at that point. Okay, so again, this right here is delta x, and this right here is delta y. Okay, so this is the scenario we're working with, but now let's translate it into some equations or formulas that we can use. And where we'll start is by noticing that you could create a vector using point P1 and point P2, right? You can make point P1 the initial point of the vector, and point P2 could be the terminal point. So it would be a vector pointing in this direction. That vector would be parallel to the unit vector, right? So vector P1, P2 is parallel to the unit vector u, and we know that parallel vectors are scalar multiples, meaning the only potential difference in those 2 vectors would be a scalar or a constant multiplied by one of them. So what we could say here is that the vector P1, P2 is equal to some scalar value, and I'm going to use h, multiplied by the unit vector u. Okay, that would be true because those 2 vectors are parallel, so they would be scalar multiples. And then if we define our unit vector u to have components of u1 times I plus u2 times j, u1 and u2 just represent the x and y components of that unit vector, then what we could do here is multiply h by both of those components. So this would be equal to h multiplied by u1 times I plus h times u2 times j. Okay, so that's one way that we could represent this vector, P1, P2, but another way that we could represent it is using delta x and delta y, right? If you're going to find a vector using 2 points, you take the coordinates of the terminal point and subtract the coordinates of the initial point. So we would take these coordinates for P2 and subtract out P1, so you'd have x sub 0 plus delta x minus x sub 0, just giving you delta x. And then you'd have y sub 0 plus delta y minus y sub 0, just leaving you with delta y. So another way that you could represent the vector p1, p2 would be with a vector that has an x component of delta x. So we have delta x times I plus a y component of delta y. So delta y times j. Okay, and so this is another way to represent the same vector that we defined before, which means that their components should be equal, right? If both of these two vectors represent vector p1, p2, then their x components and their y components should be exactly the same, meaning that delta x would be equal to h times u1, and delta y would be equal to h times u2. Okay, again, all I'm doing here is setting these x components equal to each other and these y components equal to each other because they must be equal if both of these vectors represent vector p1, p2. And so that's good, but at this point you're probably wondering, what does this do for us? What is the point of this? Well, now what we can do is actually set up a calculation for the directional derivative at this point in the direction of u using the limit definition of a derivative, and these definitions of delta x and delta y will help us properly set up that definition. And so here's what I mean by that. Remember that just a little bit ago, we were talking about how as point P2 gets closer to point P1, that this secant line between those 2 points would become the tangent line at this point, which would have the slope in the direction of u. That would be our directional derivative. And so what we're describing there is essentially the limit definition of that directional derivative. And so we would look at the limit as the change in x and the change in y approach 0, right? As point P2 becomes point P1, both of those changes in those coordinates of x and y would have to become 0. So this is going to look a little bit weird at first, but we're going to have the limit as delta x approaches 0 and as delta y approaches 0. And if you remember from calculus 1, in our limit definition, we're really looking at the limit as the independent variable approached 0 of the change in the rise divided by the change in the run, because slope is rise over run. And so in this case, the change in the rise, or what would go in the numerator of the expression for our limit, would be the change in the z values between this point and this point along the curve, right? That curve that is created when the plane cutting through this line slices through the surface. Okay, so even though we're imagining point P2 getting closer to point P1, we're also imagining this point getting closer to this point along that curve on the surface. And so from that point to this point, there would be a change in the value of z, or the output of the multivariable function. Okay, so we would have the output for this point that has the same x and y coordinates of point P2, these coordinates right here, and then we would subtract the output of the function at this point, which has the same x and y coordinates as point P1, these coordinates right here. So the change in the rise, or the change in the dependent variable z between those 2 points, would be represented by f of x sub 0 plus delta x, comma, y sub 0 plus delta y minus f of x sub 0, y sub 0. All right, we have the function output at this point minus the function output at this point. That will be the difference in the value of z. And so that takes care of the change in the rise, but what about the change in the run? Or really, you can think of it as the change in the independent variables. Well, in this case, that would be the measurement from point P1 to point P2 here in the xy plane, right? This measurement right here would be the change in the independent variables, and that would account for both the change in the x values and the y values. But how would we represent that distance? Well, what we actually have here is a right triangle, right? This would be a right angle right here. And so if we were to look at that triangle a little bit closer here, this would be our right angle. You have the change in x for one side of the triangle, and then the change in y for the other side, and the hypotenuse represents that distance between point P1 and point P2, or really that's the total change in the independent variables between those 2 points. So what we can do is find a way to represent that distance using the Pythagorean theorem. That change in run would be equal to the square root of the sum of these 2 sides squared, okay? Because a squared plus b squared equals c squared, and c in this case would be the length of this hypotenuse, and then a and b would be delta x and delta y. So delta x squared plus delta y squared would be equal to c squared, and then if you take the square root of both sides, you find that c, the length of the hypotenuse, is the square root of delta x squared plus delta y squared. Or another way of viewing this is remember that we defined vector p1, p2 as the vector between those 2 points, and so that vector's magnitude would actually be the distance between those 2 points. Okay, so you could also just take the magnitude of this vector, which would be the square root of the sum of the components squared. Okay, so the change in the run, or the distance between those 2 points with respect to x and y, would be the square root of delta x squared plus delta y squared. Okay, and so this is our initial setup for the limit definition of a directional derivative, specifically the derivative at a point on a surface in the direction of a unit vector, but we can make it look a little bit nicer. Specifically, what we can do is get the definition to be in terms of that scalar of h, because h is related to both delta x and delta y, right? We can replace delta x here with h times u1 and delta y here with h times u2, and then the denominator here, we can simplify this using these definitions of delta x and delta y. Let me show you that here. We would have the square root of delta x squared, so you'd have h times u1 both being squared, so you'd have h squared times u1 squared, and then plus delta y squared, so you'd square delta y, which would be the same as squaring h times u2. So you'd have h squared times u2 squared. Okay, and so then simplifying, these two terms have a common factor of h squared, so you could pull that out, and so you'd have the square root of h squared times u1 squared plus u2 squared, but then the square root of h squared is just h, so this is equal to h times the square root of u1 squared plus u2 squared, and the square root of u1 squared plus u2 squared is just the calculation for the magnitude of our unit vector u, right? If you were to take the magnitude of this vector, you would take the square root of the sum of the components squared. And we know that this is a unit vector, right? We've defined it to be so, which means that that magnitude would be 1. So this just becomes h times 1, which is h, okay? So that denominator we could replace with just h. And so here's the bottom line. Here's what we've been working towards this entire time. We can rewrite this limit to not involve delta x and delta y, but rather h. And so we will have the limit, but as h approaches what? Well, it will be as h approaches 0. Okay, and that makes sense because if h approaches 0 in these two equations, so would delta x and delta y, right? As h approaches 0, or as it becomes 0, you'd have 0 times u1, so just 0, so delta x would also be approaching 0, and the same thing for delta y. As h approaches 0, this side of the equation would become 0, and so delta y would also approach 0. So it's safe to make this jump. The limit as delta x approaches 0 and as delta y approaches 0 could be rewritten as the limit as h approaches 0, but then we're going to write everything in terms of h. We already determined that the denominator is just equal to h, so we'll have h down there. And then in the numerator, remember that I said that we can replace delta x and delta y with what they're equal to in terms of h and those components of the unit vector. So altogether, we have f of x sub 0 plus delta x, which is h times u1, and then y sub 0 plus delta y, which is h times u2, and then we subtract f of x sub 0, y sub 0. And that right there is the result that we've been looking for. What we have found right here is the limit definition of a directional derivative. It describes the slope at a point on a surface with x and y coordinates of x sub 0, y sub 0 in the direction of a unit vector with components of u1 and u2. Okay, and so furthermore, to summarize, the definition of a directional derivative is this: the derivative of a multivariable function, f of xy, in the direction of a unit vector u with components of u1 and u2 is represented by this formula. And what we have here is the notation for a directional derivative. We have capital D sub the unit vector u, or the way that I would read this is the derivative in the direction of u of f of xy is equal to the limit as h approaches 0 of f of x plus h times u1, y plus h times u2, minus f of xy, all divided by h. All right, so just like we had a limit definition for a regular derivative in Calculus 1, we also have a limit definition for a directional derivative here in Calculus 3. And this could also be applied to partial derivatives, because if your unit vector is the standard unit vector in the x direction I, then this calculation would result in a partial derivative with respect to x. And in the same way, if this unit vector was just the standard unit vector j, which is the standard unit vector in the y direction, then the result of this calculation would be the partial derivative with respect to y. Okay, it's just that now with this definition, we can account for other directions as well. We don't just have to use the standard unit vectors I and j, we can use any unit vector to help us find the derivative in any direction. Okay, but now some good news and some bad news. I'll give you the bad news first. We're really not going to use this definition of a directional derivative, which maybe begs the question, why did we even find it? But we go through the process of finding this formula because it should hopefully give you a better idea of what we're doing when we're finding directional derivatives, but it's also helpful because it will help us find an easier way to find a directional derivative, which is actually the good news. We don't have to use this formula. There is a better way. There is a much quicker way to find a directional derivative, which is what we're going to look at next. Alright, so just as with regular derivatives in Calculus 1, we don't always have to use the limit definition. In fact, we prefer not to use it. We like to use our other derivative rules. We can do a very similar thing with directional derivatives. We don't need to use that limit definition that we found, although it will help support that the formula that we will use will do the exact same thing. Alright, so what we're going to do is consider the same directional derivative, but from a different approach. And so here's what it's going to look like. What we're going to do is consider a function, g of h, that is equal to a multivariable function, f of xy, where x is equal to x sub 0 plus delta x, and y is equal to y sub 0 plus delta y. Now at first this seems a little bit weird because g of h is a function of h, but it's defined as a multivariable function of x and y that don't seem to be in terms of h. But if you remember from earlier, we defined delta x as being equal to h times the x component of the unit vector u, so u sub 1, and we defined delta y as being equal to h times the y component of the unit vector u sub 2. So we could also write x is equal to x sub 0 plus h times u sub 1, and then y is equal to y sub 0 plus h times u sub 2. Okay, so really what we have here is a composite function that we've been given the different pieces for. Right, g of h is a single variable function, but we're defining it as a multivariable function, f of xy, where x and y are both defined in terms of h. Okay, so this should look very familiar because it's the type of functions that we worked with when we learned the chain rule for multivariable functions, which is actually what we're going to use here to develop a formula that makes finding a directional derivative much easier than if we were to use the limit definition. Alright, because what we can do here is draw a derivative tree, starting with the dependent variable. We don't have it written out explicitly, but you could think of it as g of h, or just the function f, which is how I'm going to write it here. We have f, which is defined in terms of two intermediate variables, x and y. So we have x and y, and then both of those two intermediate variables are defined in terms of one independent variable, h. Okay, x sub 0 and y sub 0 are just constants, and u sub 1 and u sub 2 would also just be constants. Alright, u sub 1 and u sub 2 are just the components of the unit vector, and x sub 0 and y sub 0 are just the x and y coordinates of the point where we want to find the slope of the tangent line on the surface in the direction of the unit vector. Okay, but then from this derivative tree, we could represent the derivative of g with respect to h, or you could think of it as the derivative of f with respect to h. Okay, using the chain rule for multivariable functions, g prime of h would be equal to the partial derivative of f with respect to x, right? We have two different paths here, and so because we have a choice, we could either go to x or y. This will be a partial derivative. We'll have a partial of f with respect to x, so we have a partial of f with respect to x multiplied by the derivative of x with respect to h. Okay, so we multiply by dx dh. It's a regular derivative because there is no choice there. X is only defined in terms of one independent variable, but then we will add our second term for the second path. We'll take a partial of f with respect to y, so I'll write that down, a partial of f with respect to y, and that will be multiplied by the derivative of y with respect to h, and that is a regular derivative. So we have dy dH. Okay, and so using the chain rule, we get this formula, but we can rewrite it a little bit. G prime of h will be equal to the partial of f with respect to x. We can represent that with a simpler notation of fx, and that will be multiplied by the derivative of x with respect to h, which we can actually calculate, right? We know what x is equal to. It's right here. X is equal to x sub 0 plus h times u sub 1. And so if we take a derivative with respect to h, this first term will become 0 because it's just a constant. And then for this term, we have h to the first power times a constant, so its derivative would just be that constant. So dx dh is just u sub 1, the x component of the unit vector. And then we'll add that to the partial of f with respect to y, which I'm just going to rewrite with a simpler notation of fy, and that will be multiplied by the derivative of y with respect to h. And we can calculate that as well, just like dx dh. We know what y is equal to. It's equal to y sub 0 plus h times u sub 2, and the derivative of y sub 0 would be 0, because y sub 0 is a constant, and then h times u sub 2, well, h is to the first power, and it's being multiplied by a constant, so its derivative would just be that constant, u2. So we have fy times u2, the y component of the unit vector, okay? Or really, to be a little bit more precise, I'm going to use the full notation for fx and fy. So we'd have fx of xy times u1 plus fy of xy times u2. And now the reason I did that is because then what we're going to do is evaluate that derivative of g prime at 0. And I know that this seems really weird at first. There seems to be no reason behind anything that we're doing here, but I promise that it will make sense in just a little bit. Because once we do this, once we plug in 0, we will have an expression that we will be able to compare to something else that will prove that this formula is the same as our limit definition of a directional derivative from before. Okay, specifically we're going to compare it to g prime of 0, because when we plug in 0 for h, what will x and y be? Well, if h is 0, you'll have 0 times u sub 1, so you'll just have x sub 0. And then the same thing for y. If h is 0, you have 0 times u sub 2, which is 0, so you just have y sub 0. All right, so what you get here is the partial derivative at that specific point x sub 0, y sub 0, which is where we would want to find the directional derivative, right? X sub 0 and y sub 0 are the x and y coordinates of that point on the surface, and that would be multiplied by u sub 1, and then we're adding that to the partial derivative with respect to y of x sub 0, y sub 0 times u2. Okay, so this is an important formula. We're going to come back to this, but now what I want to show you is that there's another way that we could define g prime of 0. G prime of 0, or the derivative of g evaluated at 0, would also be equal to the following formula. And I will explain where this comes from, but I'm going to give it to you first. We have the limit as h approaches 0 of g of h minus g of 0 divided by h. Okay, now I'm sure it's not clear where that came from, and so let me show you where it does come from. It is based on an alternate form of the derivative definition from Calculus 1. All right, our regular definition, remember that if we had f prime evaluated at some constant c, that the limit definition was the limit as delta x approaches 0 of f of that value of x, c, plus delta x minus f evaluated at that constant divided by delta x, right? It's the same thing as f prime of x, except we're evaluating f prime of x at some value of c. So each of the x's are replaced with c, but this would be our limit definition as you're used to seeing it. But if we were to let x be equal to c plus delta x, then as delta x approaches 0, which is what we're looking at in the limit, right? As delta x approaches 0, in this expression, if this becomes 0, x becomes equal to c, right? X approaches c. So what we could do is rewrite this limit definition like this. F prime of c would be equal to the limit as x approaches c, right? We just showed that as delta x approaches 0, x approaches c, so we can replace that. And then since we let x equal c plus delta x, instead of having f of c plus delta x, we'll just have f of x. Okay, we're just going to substitute x in for that expression, giving us f of x minus f of c divided by delta x, which if we let x equal c plus delta x, solving for delta x here gives you that delta x is equal to x minus c, right? You would subtract c from both sides of the equation, giving you delta x is equal to x minus c. And so instead of delta x in the denominator of the definition, we can write x minus c. This is an alternative way of representing the definition of a derivative from Calculus 1. And this is the formula that's being used right here. We have g prime of 0, so 0 would be c in this case. It's the constant or the value that we're evaluating this derivative at. And so we'll have the limit as h, the independent variable for the function, right? Before it was x for f, and x is approaching that value of c. So now we have h approaching that value of 0. And then you have f of x, or g of h, minus the function evaluated at that constant. So we have g evaluated at 0, divided by the variable minus c. So in this case, the variable is h, and we would be subtracting 0, so it's just h. Okay, so that's where this formula comes from. We're just defining g prime of 0 using an alternate form of the limit definition of a derivative. And so why do we do that? Well, remember how we defined g of h? G of h is equal to f of xy, where x is equal to x sub 0 plus h times u sub 1, and y is equal to y sub 0 plus h times u sub 2. So this would be equal to the limit as h approaches 0 of that function f of x sub 0 plus h times u sub 1. That's what x is. And then for y, we have y sub 0 plus h times u sub 2. And then we subtract g of 0. And if you plug 0 into this function, you would have to first plug it into these definitions for x and y. If h is 0, these two terms are 0. So x is just equal to x sub 0, and y is just equal to y sub 0. So in other words, g of 0 is just equal to f of x sub 0, y sub 0. All right, and then we're dividing that by h. And now what do we have here? Well, this is our limit definition for a directional derivative, right? This is the exact same formula that we found earlier, right? You can go back and compare this formula to our limit definition, and you will see that it is exactly the same. So what this means is that if g prime of 0 is equal to the limit definition of a directional derivative, given how we define g of h, then this other formula that we found for g prime of 0 would also be a way to find the directional derivative, right? G prime of 0 is equal to the partial derivative with respect to x times u sub 1 plus the partial derivative with respect to y times u sub 2, but it's also equal to the limit definition of a directional derivative. So instead of using the limit definition, we can just use this much nicer formula. All right, we can just say that the derivative in the direction of vector u for a function f of xy is equal to the partial derivative with respect to x times the x component of the unit vector plus the partial derivative with respect to y times the y component of the unit vector. And that is the formula that we will use to find a directional derivative. It will be so much nicer than if we were going to try to use the limit definition. Okay, so to summarize, this is our formula for a directional derivative. The derivative of f of xy in the direction of a unit vector u with components of u1 and u2 is represented by this. The derivative in the direction of u of f of xy is equal to fx times u1 plus fy times u2, where fx and fy are the partial derivatives with respect to x and y of f of xy. Okay, and so if you want to know the slope at a particular point on this function f of xy, you would plug in the x and y coordinates for that point into this directional derivative. That will give you the slope of the tangent line at that point on the surface in the direction of this unit vector. Okay, but now there is an alternate way to represent this formula, because there is another way that we could represent this unit vector, and so here's what that looks like. We learned that a unit vector could also be represented like this. The unit vector u is equal to cosine theta times I plus sine theta times j. In other words, the x component would be cosine theta and the y component would be sine theta, where theta is the angle that the unit vector u makes with the x-axis. So if you're given an angle that the unit vector makes with the x-axis and you want to find the directional derivative, what you could do is use this formula instead, where rather than using the components of the unit vector, u1 and u2, you don't even need them, you just need the angle. you could find the directional derivative by taking fx times cosine theta plus fy times sine theta. Okay, and that would give you the same answer as if you just knew the components of that unit vector without the angle. Okay, and so with that, that is everything you need to know about directional derivatives, at least for right now. Later on in Calculus 3, we will extend this idea to more variables, but you're going to have to wait for that. And so to finish off this lesson, I do want to take a look at two examples where we will find a directional derivative at a point on a multivariable function. Hey, real quick, before we get to the next part of this lesson, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so for this example, we want to find the directional derivative at the point 2, 1 in the direction of the vector that makes an angle of theta equals pi divided by 3 with the x-axis. And our multivariable function, f of xy, is equal to x cubed minus 2x squared plus y to the power of 4. All right, and so the first thing I'm going to do here is write down the formula that we will use to find this directional derivative. And so remember the formula: the derivative in the direction of the unit vector u for this function, f of xy, is equal to the partial derivative with respect to x of that multivariable function multiplied by the x component of the unit vector plus the partial derivative with respect to y of the function multiplied by the y component of the unit vector. Okay, and so let's begin by finding the first partial derivatives of this multivariable function. That's something that we are very familiar with doing by this point. So let's begin with fx, the partial derivative with respect to x. And looking at our function here, the first two terms are entirely in terms of x, so those are pretty simple derivatives. Just use the power rule for both of them. For x cubed, we get 3x squared, and then for negative 2x squared, we get negative 4x to the first power. All right, in each case, I multiplied the exponent down and subtracted 1 from the exponent. And then for the last term, y to the power of 4 would be a constant because we're taking a partial derivative with respect to x, so its derivative would just be 0, which means fx is just equal to 3x squared minus 4x. All right, but then for fy, the partial derivative with respect to y, these first two terms are in terms of x, so they are just constants whose derivative is 0, which means we only have to worry about the last term here, and we can take the derivative of y to the power of 4 using the power rule, and we get 4y cubed. Okay, so those are the partial derivatives that we needed here, but now we also need the x and y components of the unit vector. But we were not given a unit vector here, were we? Instead, we were just told that we want to find the directional derivative at this point in the direction of the vector that makes an angle of theta equals pi divided by 3 with the x-axis. And so even though we're not given the specific unit vector, we are given an angle that is made with the x-axis that we can use to set up the unit vector we need. And so remember, we can find a unit vector using an angle that it makes with the x-axis. The x component is cosine theta, so that's multiplied by I, and then that is added to the y component, which is sine theta, and that's multiplied by j. And so we know that theta, in this case, is pi divided by 3, so we will have that the unit vector is equal to cosine of pi divided by 3 times I plus sine of pi divided by 3 times j, and cosine of pi divided by 3 is 1/2, so we have u is equal to 1/2 I plus sine of pi divided by 3, which is the square root of 3 divided by 2, and so that's multiplied by j. All right, and so what we have found here is that u1 will be 1/2 and u2 will be the square root of 3 divided by 2. So altogether, the directional derivative for this multivariable function in the direction of this unit vector will be equal to fx, which is 3x squared minus 4x. So I'm going to write that in here. 3x squared minus 4x multiplied by u1, which is 1/2. So we'll multiply by 1/2, and then we'll add that to fy, which is 4y cubed. And so I'll write down 4y cubed, and that will be multiplied by u2, or the y component of the unit vector, which is the square root of 3 divided by 2. So we have the square root of 3 divided by 2. All right, and so then to simplify, I'm just going to move this 1/2 out front. There's no reason to distribute it, so we have 1/2 times 3x squared minus 4x plus 4y cubed times the square root of 3 divided by 2. You can divide this 4 by 2 and get 2. So we have 2 square roots of 3 times y cubed. And that right there would be the directional derivative itself, at least in terms of x and y. But we do want to evaluate it at a particular point, right? What we have here is essentially an equation that gives us the slope of the tangent line at any point on this surface in the direction of this unit vector, but we want to know the directional derivative at this specific point. So to do that, we have to plug in this value of x and this value of y into the directional derivative. So let's do that here. We want to find the specific slope at that point, so we will evaluate the directional derivative for the function at 2, 1, right? That is the point that we're working with, and that will be equal to 1/2 times 3 times x squared, where x is 2, so we're multiplying by 2 squared minus 4 times x, so we'll multiply by 2, plus 2 square roots of 3 times y cubed, where y is 1. So we're multiplying by 1 cubed. All right, and then simplifying. 2 cubed is 4, 4 times 3 is 12, so we have 12 minus 4 times 2, which is 8. So 12 minus 8 is 4, giving us 1/2 times 4 plus 2 square roots of 3. And then 4 times 1/2 is 2. And so I'm just going to rewrite that right here. We have 2 plus 2 square roots of 3, which would be the exact value of the slope of the tangent line at this point on this surface, but just in the direction of this unit vector. Okay, and as a decimal, 2 plus 2 square roots of 3 is approximately equal to 5.46. And some more decimals, so that gives you an idea of what the actual value of that slope is. Okay, but now we're done. That's how you find a directional derivative at a point on a surface, given a particular direction. In this case, we were given an angle that a vector makes with the x-axis, but sometimes when you want to find a directional derivative, you won't be given an angle, but rather just a vector. And so to close out this lesson, I want to take a look at one more example where that is what we were given. For our last example, we want to find the directional derivative at the point 0, 0 in the direction of vector v. And we are given the multivariable function f of xy is equal to sine of 2x plus y, where vector v is equal to 3i minus 4j. Okay, so this time around, we're not given an angle that the vector makes with the x-axis, so our way of finding the directional derivative here will look a little bit different, although it's mostly the same. It'll just differ a little bit in regards to the unit vector. But we'll take a look at that in just a second. The first thing I want to do here is just write down the formula that we're going to use to find this directional derivative. The derivative in the direction of the unit vector for this function, f of xy, will be equal to the partial derivative with respect to x of that function times the x component of the unit vector plus the partial derivative with respect to y times the y component of the unit vector. Let's start by finding fx, the partial derivative with respect to x. And so looking at our function here, we have sine of 2x plus y. X is inside the sine function, so we do need to take the derivative of it. Specifically using the chain rule, we'll take the derivative of the outside function and then multiply by the derivative of the inside function. And the derivative of sine is cosine, so we'll have cosine of 2x plus y, and then the derivative of the inside function would just be 2, right? The derivative of 2x is 2, and then y, with respect to x, is a constant, so its derivative is 0. So altogether, the derivative of the inside function is 2 plus 0, which is 2. All right, so I'm going to move that 2 to the front, and we'll have 2 times cosine of 2x plus y. that would be the partial derivative with respect to x. Now, let's find the partial derivative with respect to y, and once again, y is inside the sine function, so we do need to take the derivative of it, and we will use a chain rule. However, this time the derivative of the inside function will not be 2, it will be 1, because now we're differentiating with respect to y, so 2x is just a constant whose derivative is 0, and the derivative of y is 1. So you'll have cosine of 2x plus y times 1, which is just cosine of 2x plus y. So that takes care of the partial derivatives. Now, let's talk about the unit vector. How are we going to get the x and the y component of the unit vector for this scenario? Well, you might be tempted to just use these components for this vector that we've been given, but you have to be careful. Sometimes you may be able to do that, but other times you won't be, because it all depends on whether you've been given a unit vector or not. Just because you're given a vector doesn't mean it is a unit vector. You have to check it, because when you're finding a directional derivative, you are required to use the components of a unit vector, not just any vector. Okay, so we need to check if this vector is a unit vector. We want to calculate its magnitude and see if it's 1. And if it's not 1, then we want to make this vector into a unit vector by dividing it by its magnitude, right? That's something that we learned how to do earlier in Calculus 3. We know that a unit vector is equal to any vector divided by its magnitude. And so that's what we are going to do here if this vector is in fact not a unit vector. So let's see what we have here. Let's calculate the magnitude of this vector. We'll take the square root of the sum of its components squared. So we have 3 squared plus negative 4 squared. So we get the square root of 25, which is 5. And that is not 1. So what we've been given here is not a unit vector. But we can turn it into a unit vector by dividing it by its magnitude, which we now have. So in this case, our unit vector will be equal to 3 divided by 5. So we have 3/5 I minus 4 divided by 5. So we have 4/5 j. Okay, we took the original vector v, divided it by its magnitude, and now we have a unit vector that we can use for the directional derivative. So let's put in all the different pieces that we know now. Starting with fx, we have 2 times cosine of 2x plus y, and that will be multiplied by u1, the x component of the unit vector. So we multiply it by 3/5, and then that will be added to fy times u2. So you'll have cosine of 2x plus y multiplied by negative 4/5. All right, so writing that down, we have cosine of 2x plus y multiplied by negative 4/5. Now let's simplify. 2 times 3/5 will be 6/5. So this is equal to 6/5 times cosine of 2x plus y. And then moving this negative 4/5 out front, we will subtract 4/5 times cosine of 2x plus y. And that right there is the directional derivative for this multivariable function in the direction of this vector that we've been given. You can use this expression to find the slope of the tangent line at any point on this surface, but only in the direction of that vector v. And so speaking of which, we want to find the directional derivative at the point 0, 0. So let's plug in 0 and 0 for x and y in our directional derivative. Doing that, we will have the derivative in the direction of the unit vector for f of 0, 0, because we're plugging in 0, 0 for x and y. That is equal to 6/5 times cosine of 2 times 0 plus 0 minus 4/5 times cosine of 2 times 0 plus 0. So for both of these two cosine functions, we have cosine of 0, which is 1. All right, so we have 1 times 6/5 and 1 times negative 4/5. So this just becomes 6/5 minus 4/5, and 6/5 minus 4/5 is 2/5, which would be the slope at that point on this surface in the direction of this vector v. Okay, and of course, 2/5 as a decimal is 0.4. So that would also be a correct answer. However you want to express it is fine. But either way, that is the correct answer to this example. All right, and so that's how you handle finding a directional derivative when you're just given a vector, not the angle that it makes with the x-axis. Yes, you could technically find that if you really wanted to. You could find the angle that this vector makes with the x-axis, but that's a whole lot of extra work that you don't need to do here. Instead, just check to see if that vector is a unit vector, and if it's not, turn it into one, and then you're good to go. You have the two components that you need to calculate the directional derivative. Alright, and so with that, that's it for this lesson. But if you do want to get some more practice, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.